In this video, we're going to discuss oxymercuration and demercuration. Now, the nice thing about this reaction is unless the professor expressly tells you, you're usually not responsible for the mechanism. What you are responsible for is knowing what the reactant is, what the product you get is, and the rules about stereochemistry, and that's about it. Now, if you're from the summer course, you'll also be responsible for knowing where OHs and hydrogens come from in this reaction, but I'll talk about that after the general rules. Now, the way oxymercuration works is you're going to start with a carbon-carbon double bond. And this reaction will turn that double bond into a single bond by adding to one end of the double bond a hydrogen and the other end an OH. The OH will be added to the higher degree carbon of that double bond, and the hydrogen will be added to the lower degree. So in this structure, I see that I have a tertiary carbon and a secondary carbon. As I said, the OH gets added to the higher degree, and the hydrogen gets added to the lower degree. Now, as far as stereochemistry is concerned, we've already talked about syn additions, we've talked about anti-additions. Oxymercuration actually can form either. It can do a syn addition or an anti-addition, which means you have a bunch of different stereochemistries you could get for your answer. So usually these don't stress stereochemistry in the answer. That said, I'm going to keep things plainer in that case. What I mean by that is we have our methyl that's still there, and on the higher degree I should see an OH that gets added. The hydrogen would be added on the lower degree. If I started drawing in stereochemistry, well, I have four possibilities. Both wedged, both dashed, one wedge, one dash, or one dash, one wedge. Four different products, and that's why they probably won't stress stereochemistry if you're required to do this question, or this reaction in a question. Now, the important thing, again, is just to remember that the OH goes on the higher degree, and the hydrogen goes on the lower degree. The other thing to know depends on whether the professor stresses it or not. In the summer course, this is almost always something you need to know, and in the main semester, it can vary. What you need to know, especially if you're in the summer course, is where does the OH come from, and where does the hydrogen come from? Well, in the first step, the H2O is what gives you the OH. The hydrogen comes from the NADH4 on the second step. So what that means for you, especially you summer students, is if they give you a modification of this reaction, and instead of saying NADH4, they say NABD4, or instead of H2O, they say D2O, you have to be able to find where that deuterium should end up. So if you see D2O in your first step, that means that instead of an OH, you should get an OD. And if you see NABD4 in your arrow, that means this hydrogen should be a deuterium. Okay? So just pay attention to that. I've seen questions on this a number of times, especially in the summer course. And that's really all there is to oxymercuration. You know your rules about degree, you know your rules about what gives you what, and you're fine. Now, after talking about oxymercuration, we now have three good reactions that allow us to, on one end of a double bond, put an OH, and on the other end, put a hydrogen. And let's just talk about those and some questions that can come about from them. So here are our three reactions that we've now learned that allow us to add a hydrogen to one end of the double bond and an OH to the other. Acid-catalyzed alkene addition, hydroboration, and oxymercuration demercuration. Each of them have their own sets of rules and tell you where that OH should go. In the case of the acid-catalyzed reactions, we've seen that they get a carbocation intermediate, and that means they're capable of doing shifts. If we were to look at this mechanism, we have an H plus in our first step, and the double bond will grab onto that H plus. That will give you a carbocation on the higher degree of the two carbons of that double bond, meaning in this case the secondary one, and that means over here your hydrogen will be placed on the lower degree. Now, if there was no higher degree carbon next to that carbocation, we wouldn't have to do any shifts, and so the H2O would just simply attach there. However, because this carbocation is a single bond away from a tertiary carbon, we're going to end up doing that hydride shift again. So the hydrogen will switch places with this carbocation, and you'll get the carbocation on the tertiary position. Now your water will come in on that carbocation, and that water comes in with both of its hydrogens, meaning when it's attached, it will be H2O positive, meaning we have one last step. We need to deprotonate it. So one more molecule of water will come in, grab that hydrogen, kick electrons onto that oxygen that is positive, neutralizing it and giving you your final answer, which will be the hydrogen put on that lower degree carbon where the double bond used to be, and then the OH being placed on the higher degree carbon where your carbocation shifted to. Okay. Now, as far as stereochemistry is concerned for this reaction, this is a reaction that will give you both syn and anti-products, meaning when this first step happens, this hydrogen can be added on a wedge or a dash. And when this water comes in, it could also be added on a wedge or a dash. So you get 4 possible products, and usually the stereochemistry of this question isn't stressed since there are 4 different products. More importantly, they want to make sure that you're aware that this kind of a reaction, this reaction that involves a carbocation, has the potential to do methyl shifts, hydride shifts, ring expansions, and so don't mess that up. These other 2 reactions, however, do not involve carbocations and their intermediates. Now, I kind of skipped their mechanisms, and usually you're not responsible for them, so I'm not going to stress it. Just know that because there is no carbocation intermediate, there will never be a shift. And what that tells you is that the only 2 carbons that will be involved in the mechanisms of both hydroboration and oxymercuration, demercuration, are the 2 carbons that have the double bond. For the carbocation involving mechanisms, we saw that shifts can occur, and so a 3rd carbon could become involved. But for hydroboration, the rule is that the OH will be placed on the lower degree and the hydrogen will be placed on the higher degree. So it's effectively opposite in terms of what goes where for both the acid-catalyzed reaction and oxymercuration. Namely, let's say we have this double bond again. The product of this reaction would simply be the OH being put on the lower degree carbon and the hydrogen being put on the higher. And now for this reaction, it is specifically only a syn product giver, meaning both the hydrogen and that OH should come in with the same stereochemistry, either both wedged or both dashed. I've only drawn one here, but the one where they're both dashed is also applicable. And as far as the oxymercuration reaction is concerned, if I were to do that reaction, well, it's the opposite compared to hydroboration. The OH will be placed on the higher degree carbon, the hydrogen will be placed on the lower degree carbon. So I would get OH up here, hydrogen over here, and like the acid-catalyzed reaction, this is a reaction that gives you both syn and anti-products. Mechanisms aside, just know that usually this isn't stressed as far as stereochemistry is concerned. The only one that stereochemistry is super important to remember on is the hydroboration reaction. This one specifically gives you syn addition. Now let's see some common questions that they ask regarding how you use these reactions. So here are 2 practice problems that I want you to give a try using what we've just discussed. Both of them are which reaction will produce the following structure as the only major product. That structure I'm looking for is the one in red here and the one in red here. So if you want to try these on your own, go ahead and pause the video. Otherwise, let's start by going through number 1. So our goal is to get the OH in this position 3 carbons away from the methyl. Let's start with reaction A, H plus and H2O. So what would happen is the double bond will grab your H plus and you'll get a carbocation. Now the first question you have to ask is where is that carbocation going to end up? Because there are 2 spots, here or here. We know the carbocation should end up on the higher degree carbon, but both of these carbons are secondary. So there's a 50-50 shot it'll go one way or the other. And that means there's only a 50-50 shot the carbocation will end up on the right spot. You'll either get it up here on the left, on the top, or you could get it on the bottom right over there. This is what we want, but we're only going to get that 50% of the time, which means choice A can't work. Choice B would put the carbocation on the tertiary position right here after we grab the proton, which means the water would get added, or the OH group would get added to that tertiary position up here, which definitely doesn't match up with what we want, so B is out as well. For structure C, The hydroboration reaction, again, puts the OH on the lower degree, but because neither of these carbons are lower degrees, are a lower degree compared to each other, there's only a 50-50 shot that it'll end up where we want. We're going to get two products with this as well. One where the OH is added to the upper right carbon, and one where the OH is added to the lower right carbon. And if we're only getting our answer 50% of the time, that's not going to be the correct answer. D. Let's see what this one would do. So oxymercuration will add an OH to the higher degree. Again, we have two secondary carbons, so neither is a higher degree compared to the other, which again means we're going to get a 50-50 shot on where that OH ends. It'll either end up on the right or it'll end up on the left. But now here is the trick of this question. This is what we want, and we get it 50% of the time, but this structure right here is actually the same structure as that. All I have to do to make this look exactly the same as that is take it and flip it like a pancake, and when I do that, the OH will be now sticking on the right. So this reaction will work. It will give us our intended product 100% of the time. Finally, this reaction right here will put the OH on the lower degree, meaning it would end up over here, which again is not the spot we want, so choice E is out. The answer to this question is D. For number 2, let's see. So the hydroboration reaction, again, that will put the OH on the lower degree carbon, meaning the OH would end up over here. That doesn't match up with what we want, so choice A is out. HCl with H2O. Now I put HCl here on purpose, but remember HCl is just an acid. It's the same thing as writing H+. If I wrote H2SO4 or H3O positive, those are all acids, they all do the same thing. They protonate this and give you a carbocation. And where will that carbocation end up? On the higher degree. So in this case, the secondary carbon over here. But remember, whenever you get a carbocation, you always have to be on the lookout for doing shifts. I have a secondary carbon a single bond away from a tertiary carbon. That means that carbocation will end up shifting to the tertiary position, and when that happens, the water can come in, attack there, and you will end up getting the OH added to that tertiary position. So choice B works. Let's look at C now. Oxymercuration adds the OH to the higher degree of the double bond. Here I have a secondary, here I have a tertiary. That means when the OH comes in, it will be added to the tertiary position. So reaction C also works. Choice D has us doing the hydroboration reaction, which we know puts the OH on the lower degree. I have a primary carbon up here and a tertiary carbon up here. So when the OH gets added, the OH will be added up here. That doesn't match up with what we want, so choice D is out. Finally, reaction E has the carbon-carbon double bond over here. And we should know right away, since this reaction never involves a carbocation shift, the OH can only end up on one of these two carbons, but this reaction definitely won't work, but just for completion's sake, this reaction adds the OH on the higher degree, which means it will be added right there. So choice E does not work. So for this reaction, your answer will be B, excuse me, will be B and C. Okay? So these are two questions I've seen in some capacity either in workshop, pre-workshop, or actual exam questions. So they're definitely worth understanding. I say this one in particular because this is a trick Dr. K loves to pull, especially in the summer course. It looks like it's a different molecule until you just flip it and realize, well, they're identical actually. So pay careful attention to that. And with that, that takes care of a lot of the reactions from this chapter.